So we have the Lewis structure to kind of help us determine how many bonds molecules could have. To take another step forward is VSEPR, or valence shell electron pair repulsion. This helps us figure out, after we figure out how many bonds, this helps us figure out what kind of shape it's going to be, or what kind of 3D arrangement it's going to be. So if it's just something, whoops, if it's just something, what do I do? There we go. If it is just one item, so let's say it was oxygen. It has 1, 2, 3, 4, 5, 6, and then let's say we had another oxygen, 1, 2, 3, 4, 5, 6. Each one has 6 valence electrons. These lone electrons don't like being alone, so they want to pair up. So oxygen does form a double bond with itself, and even though it's a double bond, it only has one bond. So even though you have lone pairs on the side, they're not really pushing anything else. They're only pushing that one single bond. So this has no other arrangement other than being a pair. So that's not that exciting. What happens if we had 2? So in the notes we had carbon dioxide, so CO2. Well, another example that looks almost exactly the same is silicon dioxide. And the reason is because silicon also has 1, 2, 3, 4. Oxygen still has 6. So initially, let's just make sure that we got this right. So if you use S equals N minus A, so the number of shared electrons equal to the noble. So let me draw one more oxygen. We have 1, 2, 3, and they all want to have an octet, so that's 24. You have 6, 6, 4, so that's 16. So they're going to share 8 electrons or 4 bonds. So we're going to have S in the middle. And remember, these guys, in the end, you just want to get rid of these single electrons. So SNA helps, but then you could just go, okay, look. This one doesn't really work. It has to cross down. But I should have just done here. I'll cheat. There we go. So it's going to make double bonds. S, double bond, O. Now, with the silicone now inside, it has no more lone pairs. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding it. Oxygen does have lone pairs, but these guys are only pushing one thing. So since the middle small atom has 2 things around it. So it has one bond here and one bond here. So even though it's a double bond, it's one thing. So it has 2 things, in this case 2 double bonds around it. It can only have one shape because they're going to try to repel each other as much as possible. And the only way it can repel each other is at the exact opposite ends. So in a case like this, it's going to be the bond angle between them is going to be 180 degrees. And that's carbon dioxide as well. CO2. They want to be as far away as possible. These right here. So let me go back. Oop, too much. These electrons that are taking that space of a bond want to be as far away as possible from each other. And the furthest away is on the complete opposite sides of the atom, of the carbon. And when it does that, the bond angle between the 2 oxygens is going to be 180. I put 100. Okay, good. 180 degrees. Okay, so that's the first one, when you have 2 things attached. Now, if we go to the next one up, I'll do VSEPR up here. VSEPR. All right. The next one up is 3 things. So in our notes, we did SO3. But you kind of do anything similar to that. So you just want 3 bonds total. So let me think. Nitrogen. But we don't want any lone pairs. So it does just work. So I'm going to stick with this instead of winging a molecule that eventually won't work. So let's do the Lewis structure first. So the Lewis structure just shows us how many bonds there are. So we have sulfur, which has 1, 2, 3, 4, 5, 6. Oxygen 1, 2, 3, 4, 5, 6. Oxygen 1, 2, 3, 4, 5, 6. Oxygen 1, 2, 3, 4, 5, 6. So we have the following. So 1, 2, or each you have 4 times 8, which is 32. 4 times 6 is 24. So they're going to share 8 electrons or 4 bonds. The least electronegative is going to be in the center. So here's our Lewis structure: sulfur, oxygen, 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 and we're kind of like, okay, well, we need 4 bonds. So how does that work? So you're going to put one more bond on one of these oxygens, doesn't really matter which one, that one. And now let's just make sure we got everything correct. So this one will have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 1, 2, and then sulfur has 1, 2, 3, 4, 5, 6, 7, 8. So this is what the Lewis structure is. You have 3 bonds, or two single bonds, 1 double bond. So if we're looking at the center, we're looking at the sulfur, it has 3 things around it. So the sulfur has 3 things around it. Because we look at this as a single item, it has no lone pairs, so it's 1, 2, 3, it's going to try to push each other away as much as possible. So even though it might not seem like the ideal thing, but if it was a flat plane and it was like this, and let's say this one's going out, this one's coming at us. So here are the oxygens. And you might think, well, wouldn't it make more sense if this came up a little bit? But then when it does, it's closer to these, so it's going to be pushed down. So if there's 3 things, it's going to look like, this is my attempt at 3D, but if you have a top view, it's going to look like this. These oxygens are pushing each other as far away as possible. So when you have 3 things, the bond angle is a planar, and when it's a plane, you have 360 divided by 3 gives you 120. So when you have 3 things around it, you have this, and this is called trigonal planar. Okay, so 3 things. That the other one was called linear because it's straight. This one's trigonal planar, and this is with 3 things attached. So when you have 2 things attached is linear. When you have 3 things attached is trigonal planar, and the bond angle is 120. What happens if you have 4 things? So 4 things, I'm just going to cheat, 4 things is going to give you tetrahedral. And I'm going to show you a bunch of different examples of tetrahedral, but the classic one is CH4. So you have carbon, 2, 3, 4, hydrogen, 1, hydrogen, 1, hydrogen, 1, hydrogen, 1. And the way I drew it, they're just going to make a bond like that. If you want to do SNA, so each one has 1, or carbon wants 8, but these guys only want 2. So 1, 2, 3, 4. 4 times 2 is 8, so it'll be 16. Actually, we have 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have 8 shared electrons or 4 bonds, and the only way to bond hydrogen is like that. Now, this is the Lewis structure, which isn't very helpful, and what we want to do is be able to push each other as far away as possible. So if we look back to 3, so if we had H, 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 so these are pushed as far away as possible, but then now we added 1 more H on top. So this was one that's going this way, this one's coming at us, but when you do that, what's going to happen is this H on top, hydrogen's going to start pushing all the other H's down. So eventually you get this 3D structure. And I'll try my best to draw a good one. So 1 hydrogen, 1 carbon, and another hydrogen are in the same plane. 1 is going into, and 1 is coming out of it. So it looks like that trigonal planar, where it looks like that. I don't have a model with me at home, but this is tetrahedral. So it's a trigonal planar that got pushed. So before it was like, see if I can do it with my finger. I don't think I can. But before it was like that, and then it got pushed down, so it looks like that trigonal here. So this is tetrahedral. This is when you have 4 things. Whoops. 4 things is a tetrahedral. So we had 1, 2, 3, 4 hydrogen, so it's a tetrahedral. All right, let's say we had NH3. It also has 4 things, but the 4th thing is kind of different. So if you look at the Lewis structure, it looks like this. Nitrogen has a lone pair, but it has this. So what's going to happen is it is also wants to be a trigonal planar at first, but when you add those two electrons right here, it's just going to push everything down. So it's going to look like this. So technically, it is still a tetrahedral because it has 4 things. So it's a tetrahedral. But the only difference is that this lone pair is not being shared with anybody. So here you have to imagine the electrons here, even though nitrogen and hydrogen are a covalent bond. Nitrogen is more electronegative, so they'll be probably closer to the nitrogen compared to the hydrogen. But the lone pairs are going to be closer to nitrogen than any of those bonds. So remember, these electrons don't really like each other, so they're trying to push each other away as much as possible. So the lone pairs can have more push than the single bond. So what's going to happen is instead of, oh, I forgot the bond angle. This bond angle is 109.5 degrees. So what's going to happen is it should have been 109.5 degrees, but it's going to push it more. So this one you don't see. But what's going to happen is it's going to squeeze these guys a little bit closer. So instead of 109, it's 107. So it's very close to 109. Technically, it's still a tetrahedral, but you only see the bottom 3. So they have a special name for it, which is pyramidal. I think I spelled it right. I'll be honest, I'm not sure. Let me cheat. Pyramidal. Oh, it's an I. Pyramidal. Okay. So it's very similar, but it's just pushed down. All right. The last one is the one that you just have to memorize. So that is water, H2O. So here's water, and you could draw it like this, but I usually draw it like this. And the reason why I draw it like this, even though it's not a correct 2D structure, it's more correct than this one. So here, when you look at here, this has 1, 2, 3, 4 things around it. So again, 4 things, tetrahedral. It needs to be a tetrahedral. So I'm going to draw my oxygen. I'm going to draw my lone pairs as the ones in plane. And then what's going to happen is you're going to have a hydrogen coming out at you and a hydrogen going into the paper. So it is exactly like a tetrahedral. So it should initially, this bond angle be 109.5 degrees. But what's happening is you have 2 lone pairs right here. And what they're going to do is, since they're closer to oxygen, closer to these electrons, they're going to push pretty hard on those 2 bonds. So instead of being 109, it's going to shrink down to 104.5. So all these have 4 things around it, and they're about 109.5 degrees. As you're adding lone pairs, though, it's going to squish the other ones together. So here you have equal pushing because they're all about the same distance apart. When you have a lone pair, the lone pair is going to push a little bit harder compared to this bonds. And then here you have 2 lone pairs and push them up. So if I summarize this, number of things. So with CO2, you have this Lewis structure. You have 2 things attached, so it's going to be linear, and it's going to be 180 degrees. When you have something like, what was the next one? SO3. So here's a Lewis structure. I'll just kind of, there we go. Should have not done that. You have here no lone pairs because 1, 2, 3, 4, 5, 6, 7, 8. 8 things are around sulfur. We have 3 things around it. So it's going to be trigonal. Oh, can't spell. Trigonal planar. And because of that, it's going to be 120 degrees. So this one technically looks more like this. So actually, I should have just erased it. Oh, undo. Should look like this. Okay, trigonal planar. The one with 4 things, CH4. So it looks like this. C, H, H. You have 4 things. Oh, I should have done a different color. Four things. So you have 4 things, so this is going to be a tetrahedral. Okay. Then you have 2 special cases. You have NH3, which is still 4 things. But instead of another hydrogen up here, it's a lone pair. And because of that, it's still 4 things. It's still technically a tetrahedral. But it's a special tetrahedral because of the lone pair. So we're going to now call it also a pyramidal. And the lone pair, like I said, pushes a little bit more. So instead of 109.5 degrees, it is 107 degrees. Okay, and the last one, H2O, is also a tetrahedral. You have oxygen, you have, I'll do lone pairs like that. You have 1 hydrogen here, 1 hydrogen here. So you still have 4 things around it. 1, 2, 3, 4. So technically it's still a tetrahedral, but because it has 2 lone pairs, we're going to call it bent. And it's going to push the hydrogens even closer together. So it's going to be 104.5. So here's all the different ones that we're going to learn. Some atoms actually could go up to 5 bonds. So when you start getting into like transitional atoms, you'll get more. But we're going to stick with 4 as the maximum number of bonds it could do because it has 8 valence electrons. So if it's 8, these are the only different types of shapes that you could have. So with 2 things, linear 180, 3 things, trigonal planar 120, 4 things, tetrahedral 105, 109.5, but there's just 2 because you can have 1 lone pair or 2 lone pairs, so they're going to have their special case. So for us, that's all the different shapes that we're going to learn, and it's going to fit in one of those things. So you just first find the Lewis structure, find how many things are around it, and once you figure that out, you can figure out whether it's linear, trigonal planar, or tetrahedral.